I am Daniel, so I'm Daniel Whitenack. I'm the lead data scientist with a company called Pachyderm, which you'll hear a little bit more about here in a bit. And I co-host an upcoming podcast called Practical AI. Today I'm going to talk about compliant data management and machine learning at scale. So being at DataEngConf, pretty much all of that title except for one word is really easy to get excited about. We all love doing data and machine learning at scale, but for some reason when I add on the compliant part, we all kind of get sad, right? And maybe a little bit concerned. So I think that that reaction is kind of telling in the sense that as data scientists, as data engineers, we're concerned that maybe we aren't being compliant and we're going to get sued, or maybe we don't understand what it means to be compliant in certain cases. We don't know if we have to be compliant to certain regulations, and we think it might be a hassle to implement what we need to be compliant. So hopefully today, with the talk, I'll give you kind of a little bit of assurance around that there are actually ways to do the things that we really love to do, like all sorts of weird deep learning stuff, but at the same time, have these workflows be compliant with ever-increasing regulation. So the first thing I'm going to talk about is what exactly we're talking about in terms of compliance. There's a lot of maybe different ideas about what that means, and of course there's a lot of regulations out there. And then I'm going to talk and kind of hopefully motivate some guidelines that really will help us build data pipelines that are sustainable over time in the midst of kind of increasing and changing regulations. And then I'll kind of present a solution and hopefully do a demo or at least show screenshots depending on how that goes, and leave a bunch of time for question and answer. So what is the compliance that I'm talking about? Of course, there's a lot of, like I said, a lot of different types of regulation out there when it comes to processing data. I don't know about you guys, but kind of the main thing that I think of when I first think of compliance are certain industries where compliance has been an issue for a very long time, right? So if you're working with like healthcare data or financial transaction data or something like that, then you're not unfamiliar with regulation and trying to be compliant. But actually, increasing, and I really don't have to tell you guys this because it's all over the news pretty much every day, we more and more are seeing regulations geared towards kind of general data processing and kind of anyone that's processing data and making algorithmic decisions. So, obviously there's a lot going on in the States right now with people talking about, how should we regulate people like Facebook, but things are already passed in the EU. The GDPR, if you're not familiar with that, has brought about a lot of regulations that go into effect, I think, like in a month. But basically, these regulations, a lot of them are geared towards kind of anyone that's processing, people's data to make decisions. And so that pretty much covers, probably most people in these three conference rooms. And so this type of general regulation is what I'm going to focus on. And so I kind of see this as a few different pieces that you could think about. Of course, there's industry-specific regulations in terms of like healthcare, financial transactions. Some of those involve, just inherently private data, like credit card numbers or social security numbers, that maybe need to be anonymized when you process them. But then there's also, like I mentioned, the idea of kind of general regulations around any type of data that you're processing, even if you're not in healthcare or finance. So that last bit is what I'm going to focus on here. If you're interested in kind of other things around anonymization and managing private data, I would definitely recommend looking at Jim Klukar's talks from Immuta. He actually spoke at DataEngConf, I think, last go around, and he has some really great insights there. But to kind of give an example of what I'm talking about, I think a good example of this is, there have actually already been people, suing Google around autocomplete. So, like you type your name into like Google search, and then it'll say like, Daniel Whitenack is a, blank, and it's going to fill in something, right? And if it might say some nice things, but maybe it says Daniel Whitenack is a fraud or something like that. Well, I mean, Google is just processing, words and data. It's not really managing like my credit card info or my social security number or something like that, but it has this complicated pipeline behind the scenes that is really feeding this autocomplete mechanism, right? And so more and more, people are concerned with what you're doing with whatever data you're processing to produce, certain results that might not ever have anything to do with processing, inherently private data, right? So that's a type of compliance that I'm going to talk about. And really, like I mentioned, there's a lot of different regulations, and I must clarify that I'm not a lawyer. I'm not trying to give you legal advice. I'm just trying to give you some examples. So, like, generally, we're seeing kind of a move towards regulations that are pushing for like transparency or explanation of all the things you did to process data to create a specific result, including like transformations and generation of data, access to data, who accessed it along the way. And so, in general, in thinking about kind of things similar to the GDPR, what we need to be striving for is the ability to say, for any particular result that we generate, whether that's like rejecting someone for insurance or creating some result for autocomplete, right? Whatever those things are, we need to be able to stitch back all of the different pieces of data and processing that actually led to that particular result being created. And so we need to have some transparency around all of those things that led to produce results. Okay, so that can be a little bit, so that's like the downer side of my talk. So we're through that, so everybody kind of take a breath. So that's the downer side, because I don't know about you, but when I think about that, I know that I don't work for Google, but I'm guessing that all of the different things that lead to that end result of the autocomplete of Daniel Whitenack is a fraud in search, it's relatively complicated. Okay? It's not just like one Python script running in the background that does one thing, it takes in one file and outputs another file, right? That's not what we're talking about here. We're actually talking about complicated pipelines. And so when we want to think about staying compliant and providing this sort of transparency and explanation, we have to think about more than the things that are generally talked about at in blog posts and in tutorials. And by that I mean we often talk about like the training bit of data science, machine learning, and AI model training, and we talk about maybe doing inferences or serving that model. But that's only a really small piece of this puzzle. Leading up to that, there's a lot of data cleaning, there's a lot of feature engineering and model selection that goes on, potentially. There's further data transformations and kind of post-processing and optimization that might be paired with training. And then, of course, there's further transformations and post-processing potentially around inference, right? And all of these different pieces of processing might be done by different systems, by different languages and frameworks, in different ways. And also, each one of these produces input and output data, right? And so if we're thinking about like needing to provide transparency into this process, there's a lot of different pieces of data and processing that we need to manage, and that we need to understand and provide an explanation for. But also, all of those things are stitched together in a certain way, right? Like if I just kind of provide someone with all this data and processing, right, they're going to have absolutely no idea how I actually got to a particular result, right? So it takes putting the right data into the right processing at the right time on the right infrastructure to actually produce a certain result. And so in thinking about like what do we need to do for this sort of pipeline in order to get to a place where we have that ability to explain our processing, where we have transparency into our processing, I've kind of come up with three things. I think that we need a framework for managing and defining these workflows that's really data and language agnostic. Because like I said, data science and data engineering is always going to involve a lot of different frameworks, a lot of different systems and languages, and a lot of different types of data. Already this morning I've heard about probably 20 different things that every person is using, right? So we need to be able to do this in some sort of unified way to even have a chance at providing transparency. But we also need to pair with that a new kind of type of versioning. Okay? So it's actually not enough in these cases to version your code. So even if you know what code you ran to, say, train a certain model, right? Your model and the corresponding inferences downstream are going to be vastly different depending on what data you fed into that model, right? Depending on what parameters you used and what sampling you used in your data. And so it's actually not enough to version code alone. We need to version data, we need to version models, and we need to version what processing was done at what time to produce what other data, right? To be able to stitch back and say, this particular result came from this particular version of my model, which was trained using this particular version of my code, which I provided input to with this particular raw data, right? And finally, this is probably maybe more obvious in the context of this talk, but of course we need to provide access controls around the data and processing that we're doing, so that we can not only say that this data came from this model, which was using this code, but we can say this particular user committed this particular change in data which triggered these things downstream and this eventual result. Okay, so those are all the things that I proposed that we need. It turns out that people have been working on this in various ways, and I'm going to present you with kind of one solution. And this is a solution that we at Pachyderm have been kind of helping clients implement. And there's a lot of people running this in production to actually stay compliant and provide this sort of transparency into their workflows. So Pachyderm, if you don't know, it's an open source data pipelining and data management layer for Kubernetes. Kubernetes, if you're not familiar, is a container orchestrator. And so Pachyderm involves a few different main features. But I'm going to kind of tie these back to the things that we were hoping to achieve in order to provide transparency into our workflow. The first thing, remember, that we wanted is a unified way to deal with all sorts of languages and frameworks that we have in our data pipelines. And because Pachyderm is running on top of Kubernetes, we can easily utilize containers for analysis. So Docker containers. So this allows us to kind of unify every stage of processing as defined by a container. And that means you can use whatever languages and frameworks you want, everything from Python and R and Java and C++ and Bash commands and whatever you want to run. All of those can be managed in a unified way. And then we combine those into kind of a data pipeline where each of those stages of the pipeline is defined by containers. And this is actually a distributed data pipeline. So actually every stage of that data pipeline, you can individually scale and manage the resources associated with it. And the other two features, so remember, the other goal that we were really striving for is a new kind of versioning system that versions both data and code. And so Pachyderm provides that via data versioning, and which filters down into this idea of data provenance, or this ability to kind of tie specific results back to all the data and processing that led to those particular results. So in my remaining time, I'm just going to kind of pull up, I have a demo running up here, which if you can't see from where you're sitting, I'll have this pulled up at lunchtime too, so feel free to stop by and talk. But this is the Pachyderm dashboard, and I've got two pipelines up and running in this Pachyderm cluster. And if I click on any one of these pipelines here, I can see one of the first things that I mentioned. So each of these is defined, each of these processing stages is defined by a Docker container, a command that's run in that Docker container, and input data that's input to that container for processing. And that's true of whatever pipeline I'm looking at or whatever stage I'm looking at. And it's not just Python or scikit-learn here. I'm using OpenCV over on this side to process images. You could use R and whatever you want. So I'm managing all of this in a unified way. It's all defined in a unified way, so it's very easy to manage. And the second thing we talked about, remember, was the data versioning and the data provenance. So if I look at one of these blue icons here, this represents, each one of the blue icons represents a different collection of data that I'm processing in my pipeline. And up here at the top, you can see that there's some metadata about the versioning of that data set. And so you can see here that I've made 3 commits of data into this data set. I can actually go back in time to any one of those and see, oh, in this one there were 2 files, right? And in my original one there was 1 file. When I actually version that data, and I'm processing version data in this data pipeline, then the result that we want, this idea of tying any result back to all of the stages of processing and data that contributed to that result, kind of comes out naturally. So for example, if I go to some result in my pipeline, these are inferences that are being made, I can see that I've had 2 outputs of this pipeline, and I can click on any version of them and see all of the upstream commits of data that led to that particular inference. So in this case, I'm doing a machine learning inference, so I can actually go back to the particular version of my model that created that particular inference. And I could do that for any result, no matter how many times I updated my pipeline, how many times I changed my model, and how many times I ran my inference. So if you're interested in more of that, definitely come and talk to me after the talk, or at lunchtime. I can show you a little bit more details. And here, I'll just go back in the slides. I tweeted these out so you can get the links as well. But you can run all of this locally. Like I said, it's all open source, so you can pull it up all on your local machine and run it locally. We have a public Slack channel if you want to ask questions and get help with these sorts of things. Here's a link to the docs and how you can contact me. So thank you guys.
Hi, thank you for your talk. I'm actually in the process of building out something similar for ETL in general, very similar in architecture, perhaps a little more functional, but in any case, I'm curious, when you retain all of those essentially Git nodes, right, do you hold on to what the machine image identifier is as well that the code is actually running on, so you have complete environment?
Yeah, so all of that, so there's actually multiple components here, right? If you want to actually reproduce something, you need the version of all of the input data, which we get from the data versioning. You need the exact code that was run in the exact environment, so that you get from the Docker image. Which ideally is tied back via its tag to the GitHub hash that includes that code. But then also in the logs that we have, I didn't show it here, but we have kind of what we call an advanced job statistics function, where you would actually be able to see for any job that ran, you would be able to see the particular data that it processed and on which nodes it processed that data. So for instance, if you were running like distributed TensorFlow or TensorFlow on a GPU or something like that, you could get the exact node and information about that. Yep.
I think this is very cool. So obviously we're operating generally on the assumption that storage is cheap nowadays, but it's not free. So
sure.
In a world where we have very large amounts of intermediate data that we're storing, and older versions of that intermediate data might get deleted for cost savings. How does that impact the sort of traceabilities? Like, what principles do we operate on?
Yeah, so a great question. So first, like in terms of the space efficiency of the versioning, we don't use Git under the hood just because it's not efficient in this way. We have our own way of versioning, which is based on content addressing your data as it comes into the system on the fly. So what that means is, like, if you put in like a million images, right, we're going to content address each of those and store it. But if you updated that data set, let's say you updated like 1,000 images, right, we're not going to store another copy of the million images like the new state, right? We're only going to copy, or we're only going to update the data that changed. So in that way, we're able to be kind of like deduping on the fly. But then in terms of like, if you actually want to garbage collect things over time, you can definitely still retain like the metadata associated with what was processed at what time by what code, for example. But if you actually delete that state of data and garbage collect it, I mean, there's nothing that we can really do, which in that case, you know, it's back to similar, you know, maybe not similar systems, but other systems that just track metadata, right? If you're just tracking metadata, then it doesn't really get you all the way to the finish line, depending on what you need in certain scenarios.
Sorry, just to kind of jump off of that. Yeah, just to kind of jump off of that. So, what's kind of the ratio in terms of storage size between inputs and resulting machine state? One of the things that I'm doing for ETL stuff, which is probably a very different ratio, is I only hang on to inputs, and then the outputs long enough to serve whatever, you know, the Hive metastore points to. For instance, I garbage collect everything else, right? So I can reproduce everything, right? So it doesn't matter. What's the ratio between input size and resulting machine state size?
So when you say machine state size, you mean in terms of like the output living on the particular node that it was processed on?
Whatever it is that you're snapshotting as the output of the task.
This is a great question. So actually all of the cluster and all of the processing, even though it's processing, you know, data, is completely stateless. So all of the data is backed in a backing object store. So as that output is generated, that's actually passed back into the object store into kind of the distributed file system, which is essentially our layer on top of the object store. So like after that processing happens, the data that's on that node for that worker is gone. It's totally gone.
When I say machine state, I mean the machine learning algo state, right? The state of that.
Okay, yeah. So I mean that depends very much on like what. So again, one of our goals is to be framework and language agnostic, and so that means that we'll version whether you're using a pickle file or protobuf or whatever it is. So it will very much depend on like your network size, whether you're saving just the parameters or the whole state of the network in, say, PyTorch or something like that. It'll also depend on the format that you're using on the output. You know, there's a lot of different formats now. So we basically don't add anything to that particular file. We just content address it and create a hash. So the only additional data in addition to the model binary would be like a single entry and a key value store.